Hi there. Today we're talking about trends and properties of the periodic table. Now it sounds sounds pretty heavy duty, and to be honest it is a lot going on, but they're also really important. There'll be a few trends we pay particular attention to, but let's start with what we know about the periodic table. Now you may or may not recognize Dmitri Mendeleev. He's called the father of the periodic table. He was the first one to recognize and to, not to recognize actually, but he was the first one to start organizing the periodic table to show the properties. And the periodic table as we have it now looks like this. Now we know that the periodic table is arranged so that elements with similar properties are in the same column, same group, same family. What does it mean to have similar properties? What kinds of properties are we talking about? So we're going to focus on about 4 in total. And the first one is going to be the atomic radius. And that, of course, is how big is the atom. The measurement is taken from the middle of the nucleus to the outer electrons. So if you think about it, there's going to be 2 factors that play into how big an atom is. Number 1 is the electron-electron repulsion. All the electrons are negative, so like charges repel. And then the attractive force between the positive nucleus and the negative electrons. Opposites attract. There's also going to be something, and that sort of plays together, something called effective nuclear charge. An effective nuclear charge is how big does the nucleus look to those outer atoms, because the outer atoms might not feel the full attractive force of the entire nucleus. And the reason for that is when we're looking at the atomic radius, of course, we're only talking about those valence electrons. The electrons in the middle, the core electrons, they are actually going to be involved in the electron-electron repulsions. So the electrons separating the outer from the nucleus are actually pushing the atom to be bigger. So that's what we mean by effective nuclear charge, is how big does the nucleus appear to the outer electrons when they have that repulsion forces in between them. So core electrons are those inner electrons, as I mentioned. The other thing about the core electrons is that they do something called shielding. And shielding is that absorption or canceling of attractive force. Now as we go left to right, as we start filling up an orbit in an atom, the shielding electrons are still the inner ones. So if I'm adding electrons to, maybe we'll hop, and we'll keep it there. As I'm adding electrons to the outer orbits, the inner orbits are staying constant, staying fixed. So the shielding is the same. Oh, there it is. That's what I'm looking for. So if I look at sodium, I've got 10 core electrons and 1 valence electron. But if I look at chlorine, all I've done is added more valence electrons. I still have 10 electrons doing the shielding. So in terms of the influence of the positive nucleus to negative electron attractive force, the repelling force, repulsion forces from sodium to chlorine are going to be constant, going to be fixed. So in your textbook, you'll find a table like this. You probably don't have your textbook with you, and that's okay. And that table looks pretty overwhelming. So let's break it down and just focus on the atoms, because that previous table had atoms and their ions. So looking at just the atoms, as I look down a column, I'll notice that the atoms are getting bigger. As I look across a row, generally speaking, the atoms are getting smaller as I move left to right. Now there's a few little hiccups along the way, but generally speaking, the trend is they get smaller. So let's talk about the top to bottom one first. Obviously the radius got bigger, and that worked for every column. One thing, of course, that's going on is I'm getting a new energy level, and those electrons that are higher energy are moving faster, but they're also going to be farther away from the nucleus. The other thing, though, going back to those core electrons and valence electrons, is that I have more of those electrons are now core electrons. So there's more electrons doing the repelling part on the valence. So I have more shielding. Left to right is a little bit more complicated, but not a whole lot. As I move left to right, generally speaking, my radius got smaller. And what was happening was left to right, I'm doing 2 things. Number 1 is I'm adding more negative electrons in the outer. Number 2 is I'm adding more positive protons into the nucleus. So I'm increasing the amount of positive to negative attraction and that's increasing my nuclear charge. And that because of the constant shielding, so I'm increasing the amount of attractive forces, but not increasing the amount of repulsion forces. Those stay the same, core electrons. Shielding is constant. So left to right, all I'm doing is making more attractive forces while holding the repelling forces constant. Now that gives me more attraction, so my radius starts to become smaller. We won't worry about those ones that seem to be exceptions to that rule. We'll just accept the basic trend and be able to understand and explain the basic trend. Okay, but I do have increase, as I mentioned, nucleus to electron attraction. If you were to graph it, you don't need to have the graph, but if you were to actually find all the list of radii and graph them, it would look like this. And you'll notice there is a couple little hiccups along the way, but generally speaking, whoops, go back one, as I go across a row, and that's the main U shape or whatever shape that is, that curve downward, that's the left to right part. Well, if I went back and looked at this table and now talk about some of the other circles on there, the other circles that go along with each element are the ions. So we're going to break it down into two parts. We're going to start with the cations, positively charged ions. And we'll notice that the cations are always smaller than the neutral. And we don't really care how much smaller. Some of them are significantly smaller. We want to know why they're smaller. So the first part of it we have to understand is that we're losing electrons. Positive cations means that we've lost electrons. We still have, though, the same number of protons. The other thing that's actually going on is that in many cases I've lost an entire energy level. But more important is I've got the same number of attractive forces, I've got the same number of protons, and they are attracting fewer electrons. So in terms of the amount of pull that each electron experiences, it's increased a little bit. I've also, because I've lost negative charges, there's less negative repulsion going on. So it's kind of like this. If I start with this sodium atom and I remove that outer electron, now with nothing else happening, I've lost that outer energy level. That's smaller. But the other thing is that increase of attraction force and a slight decrease in repulsion force, and my atom will get smaller yet. But if I look at the anions, if I go to the other side of the periodic table, to the nonmetal side, I'll notice that the anions, the negatively charged atoms, negatively charged ions, they're actually getting bigger. So why is that? Well, probably the opposite is true, but let's look at it in a little bit more detail. We start out by gaining electrons. So right away, I'm increasing the amount of electron-electron repulsion. More electrons means more repelling forces. But I'm also not increasing the amount of attraction forces. So the same protons are in there. So now the amount of attractive force that each electron is able to feel has decreased because the proton forces are spread around a little bit more. That's not the best way to put it, but it works. So I now have weaker attractive forces, which causes my atom to grow and get larger. Next trend we're going to look at is something called ionization energy. And it's important to understand what ionization energy means because that's going to play into it a little bit later. It's the energy required to remove. It's always removing. Now I can remove an electron from anything. It might be hard to do, but it's possible. So it's important to understand that even elements that generally like to gain electrons, we can remove electrons from them. But it's always the amount of energy required to remove. So in order to remove an electron, I have to overcome attractive forces. And that's pretty easy to think about, which means that if an electron has strong attractive forces, then it's going to take a lot of energy to remove it. If the electron in that atom has weak attractive forces, then it's going to be easier to remove it. On the other hand, I think I said that opposite of what I just put up there. Okay, but you're reading and listening at the same time. The graph actually looks like that. And one thing about the graph is that box that I'm showing now, that's your left to right. And you'll notice it more or less as you go across the periodic table. There's a couple of exceptions, but as you go across the periodic table, it gets harder. On the other hand, if I look at going down a column, it's getting slightly easier each time. So there's our trends. Top to bottom, ionization energy decreases. That was the second box that we looked at. Left to right, it increases. That was the first box. I don't know why I put it in that order. Now what's happening is, and we'll use our radius to explain this, smaller atoms hold their electrons more tightly, and the more tightly they hold their electrons, the harder it is to remove. Bigger atoms hold their electrons more loosely because those atoms or those electrons are already farther out, so there is less attraction to the nucleus. Now, rather than giving you more detail about that, I'm going to ask you a couple of questions. One question is this: why does potassium always become +1 in compounds? It never becomes -1, it never becomes +2. It's got lots of electrons, 19 in total. Why does it always become +1? Whereas the atom right beside it, calcium, always becomes +2. On the other hand, on the other side of the periodic table, in nonmetals, they don't normally become cations, they don't normally become positive. I just said that we can take electrons away from them, but why don't they in normal conditions? So those are a couple questions I want you to think about, and we can use the concept of ionization energy to explain that. Now, this graph is actually even a little bit worse than the previous one, but this compares radius with ionization energy. And what I want you to do is notice that as we look at a radius, a bigger radius has a lower ionization energy. So the ionization energy is the blue line and the radius is the red. And as you move across the table, every time the radius gets bigger, the ionization energy gets smaller. Every time the radius gets smaller, ionization energy gets larger. Where are we at? 4? Third? Yeah. So radius, that's ionic radius, ionization energy, and now electronegativity. And that'll wrap it up. Electronegativity is defined as the the attraction force, the tendency for an atom to attract electrons. So it's kind of like an attractive force. How strongly does an atom attract electrons? Incoming electrons. However, we can also use that to talk about how strongly it holds onto its own electrons. The ability to attract electrons, that will actually depend on a couple of things. Number one is the nuclear charge, because it's the positive nucleus, of course, that's going to be attracting the electron in the first place. And the second thing is the radius, because how close can that incoming electron floating around in nowhere land get to the atom before it starts to really feel that attractive force? So in other words, smaller atoms tend to have a higher electronegativity. Larger atoms tend to have a smaller one. So the trend, if you were to look top to bottom, atoms are getting bigger. Those electrons are getting farther away. Those electrons are less attracted to its own atom, so new electrons coming in will also be less attracted. Whereas left to right, our electronegativity increases. As I go over to, which way am I going? Should be going that way on your periodic table. As I move to the nonmetal side, my atoms are getting smaller because the attractive force is getting stronger. So not only is the attractive force getting stronger for that atom, but for new electrons coming in, the attraction force will be a little bit higher as well. If you were to graph it, and I won't ask you to, it looks like that. Slightly smoother curve than the ionization energy, and we're not going to start layering the things on top of each other. One thing to be aware of with electronegativity, the noble gases, so your group 18, your helium, neon, argon, and so on, those atoms have a zero electronegativity. They do not attract electrons into themselves. And if you look at a periodic table that has electronegativity values, it will not list them for those elements. But you'll notice left to right, we have the electronegativity increasing, and top to bottom, it's decreasing. That wraps it up for the trends. Now, what we're going to do, though, is because we know that the properties of an element, properties of a substance for that matter, depend on its structure, we now know a little bit more, I'm having a good time today, now we know a little bit more about how structure influences properties and what kinds of properties get influenced. And we'll be using this information in class. It's going to help us with bonding, and as we go from atoms now into molecules, or compounds would be a better term, and a lot of things going further from that. I'm going to stop now. We'll talk to you in class.